Hey folks, alright, well I wanted to get into talking about optimizations, and we'll be spending a fair amount of time on this because it is a big part of trying to generate effective code for the target platform. So this time around we're just going to go through some general overview of things, and then we'll start getting into specifics in the material for next week. Let's see, where are we here? Again, the idea is we've got our source code. We go through this process of tokenizing it, parsing it, doing all sorts of analysis, generating some kind of internal representation, and then eventually we want to produce the code in the target language. But usually there's a whole variety of different optimizations we can apply at different phases as we work on this kind of internal or intermediate representation, where we're going through and saying, okay, well, let's transform it and do these optimizations. And okay, now let's transform it some more and do more optimizations. And now let's transform it some more and do more optimizations. And then maybe we'll take it and generate sort of target code in the actual language. If we're going for assembly language, we actually generate the assembly language for the target platform. And then we might look at that assembly language and say, okay, now can we optimize that assembly language I've generated and start doing transformations that are specific to that. So we'll have all kinds of different layers of transformations, and they'll deal with all sorts of different layers of the code as well, right? Transformations that just focus on looking at one specific sequential block of code, transformations that look at, taking an entire loop or something along those lines, transformations that look at an entire subroutine, transformations that look at the program as a whole. So there are all sorts of different aspects of this that we want to try and address. And again, there's going to be a lot of kind of cross-referencing back and forth between the different sections and some of the things. I mean, we've looked at some optimizations as we looked at the code generation portion in the last couple of weeks. So we'll see how we go here. Again, there's lots of different ways that kind of room for optimization creeps in. We've got code that the programmer originally produced that might not have been optimal. The programmer might have left in unreachable code, and they might have all kinds of redundancies in there, and there just might be a variety of different ways that original code could be improved. And then as we go through and we take their original code and we transform it into this sort of internal representation, the techniques that we use to do that transformation tend to focus on, taking an instruction or a specific code structure and transforming that in a fairly generic way. So, here's a for loop, let's transform that for loop. And it's not focusing too much on the code that surrounds that for loop. It's not looking at much of the environment of that for loop. It's just focusing on that one transformation. So that transformation might make sense in a kind of generic sense, and you get a valid transformation, a valid translation into this intermediate form. But there might be a better way to do it if we look at the things that come before and after the for loop, or the things that the for loop uses. So that's another area where these transformations might come from. And then on the target language itself, there might be special things about the target language instructions that are really easy to use in a highly efficient way. Or there might be other instructions and things that are on the target platform that we want to try and avoid because they cause problems, or combinations that we want to try and avoid because they cause problems. So there are all sorts of different layers that we'll try and consider here. All right, again, when we talk about optimization, most of the time people kind of have execution speed in the back of their mind, but there are, again, and we've mentioned this before, a number of other things that we could try and optimize for, right? We might be trying to reduce the total amount of memory used, or we might want to try and just reduce the number of times we're reading and writing to and from memory. Or we might want to try and minimize the size of the executable that's being produced. If we're targeting a machine that's got limited space for our executable to sit in, then again, it's important. We might be trying to optimize for response time and accept trade-offs in other areas if we can make sure that we can guarantee a fast response time as it executes. It's possible that we're even worried about the time taken to compile something in the language. Well, that's probably a lower probability, usually less of a concern. just because the compilation is usually a one-time thing, whereas or at least a rare thing, and you kind of compile once, run many sort of idea. So usually that's not a major consideration. And again, quite often we're looking at trading off, getting a boost in one area and accepting a penalty or a hit in another area to get that, or other areas to get that. So we're looking at these trade-offs all the time. Now there are a ton of different specific ways that we can try and optimize. Places where, patterns where we recognize there's opportunities for improvement. We've seen some of these already. If you can do things like eliminating redundant computations, right when we went through looking at working with loops, going through sequential access of loops, we saw that there are a lot of values that we don't have to compute over and over and over again. We can reuse it. We looked at the idea of expression trees and saying, well, if we've got each intermediate value stored in a temporary register someplace, or a temporary variable someplace, then we can often eliminate the need to recompute something and just reuse that data we've already got stored. Steps to try and reduce how often we load something from memory. If we've got a variable x in memory, I don't want to be constantly taking it out and putting it back and taking it out and putting it back. Is it possible for me to reduce some of the redundant loads that I'm doing? Can I take advantage of the memory hierarchy? If we've got a really high-speed cache, and then we've got a variety of different layers of storage access speed available to us, can we take advantage of that? Can we go through and use things like inlining of functions? If I've got a function that's only called once or rarely called, then does it make sense to inline it instead? Lots of different things we can do in terms of trying to optimize loops. We might unroll it and say, okay, well, instead of actually having this as a loop, maybe I'll just take it as, if it's a loop that's going to execute 5 times, maybe I'll just take it as that set of instructions 5 times in a row. There are times when that might be beneficial. We might look at splitting a loop up into multiple little tiny loops if we can take advantage of things that way. Maybe there's one part of a loop at the beginning or the end where we can take advantage of some optimizations if we split it apart from the rest of the loop. We can look at inverting loops, right? You're reversing the structure of it. Instead of top tested, go to bottom tested, or vice versa. If we've got nested loops, we can look at swapping the inner loop and the outer loop, right? Make the inner loop the outer loop and the outer loop the inner loop. There are times when that's going to make sense if it doesn't change the behavior of the program from an observable point of view. Getting rid of dead code, unreachable code, unused variables. Doing things to reduce the amount of branching and amount of jumping that we're doing. Taking steps to see if we can parallelize anything. Seeing if we can take chunks of redundant code and replace them with a subroutine that we call. Right? All sorts of opportunities to try and improve the code. Now, this does assume that when we do these transformations or optimizations, as far as the user is concerned, the program still seems to behave the same way. Right? It might be faster or use less memory or whatever it might be, but the actual functionality appears the same. So we want to ensure that the changes produce equivalent behavior. So as far as we're concerned, if the results are identical in the context of the program, right, if you can't observe a difference in the behavior in the context of the program that we're trying to run, then the results are identical. That's what we're really focused on. One of the things that kind of, as an aside, I'm not sure where we want to fit this in the great scheme of things, but as we do these transformations, one of the things that we're doing is moving the eventual generated code further and further from the original representation, right? Every time we do a transformation, we're kind of adding one more layer of abstraction between the original code and the code eventually produced. So if somebody is going and looking at the code that's produced in the end and trying to debug something and relate it back to the original source code, the more optimizations and transformations we do, the harder that can tend to become, because it's less and less obvious how the code that was produced ties to the original source code. But that's just something to keep in the back of the mind. Now, as we go through, I mentioned that there's a lot of different layers of optimizations that we can perform in terms of what chunks of the program or what scope of the program are we looking at. So what we'll do is divide it up into kind of a few major groups. We'll take a look at local optimizations, where all we're looking at is one of those little sequential blocks that we talked about, where we've got a unique entry point, a unique exit point, and a bunch of sequential instructions in between. And so we'll look at operations that we can do to try and optimize that. And then we'll distinguish that from regional operations, where we expand it beyond just one of these sequential blocks. So including some branching and jumping and whatever might be going on around a block, some initialization and things. So this is where you can start looking at loops and ifs and elses and switches and things, where you've got this bigger logical block that we're trying to deal with and trying to perform optimizations on. Then we'll expand that another layer and say, okay, now let's take a look at intra-procedural or subroutine level, where we look at an entire subroutine and the kind of optimizations we can perform there. Now, in kind of the historical literature for this, this is often referred to as global optimizations. That doesn't mean global in the sense of the whole program. They're talking about global in the sense of a subroutine. So the terminology I find misleading, but I will try and refer to them as kind of intra-procedural or subroutine level optimizations. But if you are doing some reading and you see this global optimization where they seem to only be looking at a subroutine, yeah, they are only looking at a subroutine. And then there's the inter-procedural or whole program optimization, where we are looking at the entire program. So we'll spend just to give kind of a brief overview of each of those today, and then we'll get into each of them in more detail next week. Later on, we'll also take a look at the code generation side and specifics related to the code generation and things like peephole, where we try and, as we take this little tiny window of looking at sets of instructions that are grouped together in the eventual generated code, and seeing if we can take these 2 or 3 instructions and replace them with something better. So that's another layer that we'll come back to much later in the process. All right, the first of those were the local optimizations. So this idea that we've got one of our single entry point, single exit point, block of sequential statements. We know that if this block runs, all of the instructions are going to run in this sequence. And because of that, it's easier to do analysis on it, right? We've got this fixed order, there's no branching, there's no jumping, there's nothing to confuse the issue. And so a lot of the opportunities for optimization in a block like that are to do things like identify redundant operations, things that we are doing multiple times in that block that we can eliminate in one way or another or reorder. Things like constant folding. If I've got a constant expression in there, then computing the result and using that instead of doing the computation as part of the execution. Again, selection of the different naming schemes that we're going to use for local variables or temporary variables or registers. One of the things that we'll get into is when we look at expression trees, are there ways that we can rearrange the expression tree to get a comparable computation in the end, but that supports better parallelization, for instance? If we've got multiple processors available, can we try and arrange things to get a faster overall computation time by divvying the workload up so that we're not a case of we've got one processor that's sitting around waiting for the other one to finish the computation that it's doing. So these are all things that we'll look at in the local optimization section. Then we'll take that and expand it beyond that, just that sequential block, and look at regional optimizations. So again, these are looking at things like loops and switches and whatnot, where we've got a structure that's got some branching in it. So somehow the compiler has to be able to come up with a way to extend blocks, so to take the blocks and rationally expand to include the relevant instructions around it. So somehow we'll have to take a look at how we do this kind of region selection. But again, there's a lot of different kinds of optimizations that can take place here, and I mentioned a few of them a little while ago. Lots of them focusing on loop optimizations. If we've got nested loops, swap the inner one with the outer one. Switch whether it's top and bottom tested. If we've got an if statement inside a loop, maybe it makes more sense from an efficiency point of view to move the if statement out and say, and so instead of having this, while blah 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 if x, then instead have an outer if x, and both sides of the if would have the while loop in it. So there are different circumstances where we might be able to recognize something we can move. Again, partitioning a big loop up into smaller ones and being able to optimize the pieces, taking a loop and unrolling it, replacing it with a bunch of sequential statements instead. If there are things that don't vary within the loop, if there are computations within the body of the loop that don't change within it, then instead of recomputing them every time, can we move them outside the loop and do them before the loop begins? I mean, all sorts of these regional optimizations that we'll take a look at. Then there's the subroutine level optimizations. So again, this is looking at the entire subroutine, so it's going to span, multiple blocks, possibly multiple regions. And here you've got a much more complete picture of what's going on, right? You can see how data is being coordinated across the different blocks and regions. So you can perform some kind of data flow analysis, see where values are coming from, where they're being consumed. You can start looking at things like, can I identify uninitialized variables? Can I identify variables whose value is computed but then never used? Can I get rid of dead code, unreachable code? Are there places where if I've got two branches that are used with different likelihood or have different amounts of code in them, can I take advantage of arranging things to take advantage of, let's say, different costs associated with branches in the target language? So maybe we've got essentially the equivalent of on this condition jump someplace, otherwise drop through and continue with the rest of the instructions. That dropping through and continuing with the rest of the instructions is a less expensive branch than the jump to someplace else. So can we take advantage of that to try and improve our processing speeds? Right? So all sorts of, again, subroutine level optimizations that we can try and take a look at. All right, and then we've got the whole program optimizations, right? Where here we really do have the whole picture, but we have to take this kind of high-level view of the whole picture. Right? The reason for abstracting all these different layers is so that we're not trying to work with all of the information about the entire program all at once, because that's computationally not feasible. So we've got these kind of pieces of information about each of the subroutines or each of the blocks or each of the different components in the program, and we're trying to coordinate all that. Again, we might have some kind of control flow or data flow analysis going on, and we're trying to evaluate for this thing as a whole, what kind of optimizations can I carry out? So again, this might involve doing inline expansions. This might be the point where we recognize that some subroutine is only called once or only called a couple of times, or where we might recognize the these chunks of redundant code across things, or repetitive code, shall we say, across things, where I can replace it with a subroutine call. This might be where we look at it and go, well, you know what? If I divide up the caller and the callee responsibilities differently, I might get an improvement. Or if I can somehow add an additional layer of administrative functionality that I can call and use instead of having it repeated in all these different code blocks, this might be something that we can take care of at a kind of global level. We might go through and, much the same way as with local variables, we try and group the ones that are used kind of together near each other in memory so that they likely wind up on the same page and whatnot. We might find ourselves doing similar things in our subroutine placement. If I've got a couple of subroutines that call each other, then I might want to place them relatively close to one another in memory in the executable so that we don't have these massive distance jumps between them when they're calling one another. So again, there are different optimizations that we might want to consider. All right, and then we'll get into, after all of this, get into some of the generated code optimizations, where once we've got our nearly complete code, we'll go through and try and improve our instruction selection, our instruction scheduling. We'll try and follow these idea of peephole optimizations. We'll look at register allocation, right, actually doing physical register allocation. We'll look at things like, are there places where we can recalculate some values instead of needing to reload them from memory? So there's a number of different optimizations that we can try and visit, again, at that just before delivery stage, if you like. All right, so a great many things that we'll consider over the next couple of weeks. For most of these, we could easily spend, days or weeks on any given aspect of the optimization. So we really are just scratching the surface of all this, but hopefully it gives you a good feel for the kinds of things that are taking place in a compiler as we go. All right, I will leave that one there for now.